Okay ji, today we are doing the DEM winding lecture. ठीक है जी, you have done, if you remember your recorded lectures which we have been going on through, you have gone through that KP, the pitch factor, and the KD, which you have done the distribution factor over there. So that KD was your distribution factor. And based on these two factors, you can find out your Kw, which is actually called as the winding factor. And I guess I don't need to tell it because this has been told in the recorded lectures that this Kp into Kd, this can never be 1. This can never be 1. The maximum value, I guess, if I'm not wrong, is approximately 0.955 for a full pitch winding with some value of G or whatever over here. Now, today what we are doing over here, there are many different types of windings for three-phase machines. Today we have the integral slot winding, and then next time I will talk about the corded pitch winding or whatever. But before I go on to that one, the first thing, very first important, whenever you are talking about windings, and if you are talking about the winding based on the wires which are coming out or not, we have two types. One is called as the open winding, the other one is called as the closed winding. Now, those of you who are a little behind in DC machines and you don't remember it, what we did in DC machines, this was a type of a DC machine winding. This was a lap winding example. And for those, you can go through on my YouTube channel and check out this lecture number 9A. It's recorded over there, but for a DC machine, this was a DC rotor or armature. And based on this DC rotor armature, the winding had to be closed. Now, why winding had to be closed? This was very important because this armature, this was rotating and it cannot have two fixed terminals that can be connected to the carbon brushes over here. So you had to have a commutator segment, and on that commutator segments, the winding would have to be connected. And at any given time, supposedly this was the positive terminal, supposedly I can take this one, this was the positive terminal and this was the negative terminal. So at any given point, entry point will be some commutator segment and leaving point will be some other commutator segment. On the contrary, if you have seen an AC machine or an induction machine, you have a winding which has supposedly A dash, and then you have a winding with B dash, and then you have the same for C dash over there. This is an AC machine winding and this is fixed. So these three terminals, it's totally up to you. You want to connect them in Y configuration or delta configuration. But when you are talking about a DC machine, the winding is closed. And by winding closed, when I draw this hole overall, you can go through the lecture overall if you want to revise this. Is a simplex lap winding. So based on this simplex lap winding, you are getting first of all this table, and based on this table, when you draw this diagram, you can see there is no connections that can be regarded as the input or the output. The input is actually this positive carbon brush. So this means that the current is actually, this is a motor supposedly, and this is the positive carbon brush. So current is going to actually enter this positive carbon brush and come out of this negative one. And at the same time, since this is a 4-pole machine, it will be entering through this and this will be leaving out from. So there are two entry points and two leaving points. But this commutator segment over here, which is connected with the segments over there, these commutator segments are constantly moving in one direction depending upon clockwise or anti-clockwise. So this means that when this positive carbon brush is connected over here at this point over here, so this is the point over there. So after some point, this 2 segment will come at this position, 3 will come at this position, 4 will come over here, 6 will come. So this is constantly moving over there. So at any given point, the entry terminals was at slot number 1 and slot number 4. A little time afterwards, then it will be slot number 2 and slot number 19. So this means LDLability is a fact which will be coming into play. But as soon as this commutator is going to move in this direction, this slot number 2 and slot number 19, this will come in contact with the positive carbon brush. So this will become an entry point. So at any given point, if you remember the lap winding, we used to draw the parallel path diagram. This parallel path diagram was actually telling you that from the positive 2 carbon brushes, the current was actually entering this one and like this. So similarly, it was entering. This is an unbalanced parallel path, but still enough to actually answer our queries over here. So these are 4 parallel paths. So at any given time, the current is entering is this path, this path, this path, and this path. But After some time, maybe this 6, 19, 16 and 9, they will be the entry part, and this 1 will come actually at this point. So all of this is rotating. So there are no two entry points fixed over there. So all of this structure over here, that is the rotor plus the armature or the commutator, is actually rotating. So this type of winding is called as closed winding, because you don't have any two terminals coming out. And since this is rotating, if I go back to your diagram, so all of these commutator segments, whatever that number may be, so this is the positive carbon brush and negative carbon brush. This type of winding is a requirement for DC machine. So you require always a closed winding for a DC machine over there. So this is a type of winding called as a closed DC winding, and this is always. Now you want to revise it on, please go to lecture number, this Chapman, lecture number 9A on my YouTube channel in the machine fundamental playlist over there. Now coming on to back to because our course is related to your induction machine design, which we have done up till now, and we are talking about the open winding or the AC winding. Now some things which we have to do before we can go on and design some winding. Your G value, which you have used up till now a lot in your design values whenever you are designing a stator slot. This G is the same thing as Q. So don't confuse yourself. G and Q, they are same thing over there. This document which I have shared with the CR Hamza. So you can actually share this document with everyone so that everyone has an idea. So in this document, they are using Q but G. So what is G actually? We have talked about previously also in the lectures that G is actually the slots per pole per phase. And this is actually equal to S divided by P into M, where P is the number of poles, M is the number of phases. I have written PH also, M also, so you don't get confused, because in this document which I have shared with you is actually using M over there, but this is the same thing as PH. So this is slots, this is slots. Now whenever you are designing a machine, an induction machine, you were always told that supposedly you have to design a machine with G equal to 4 or G equal to 5 or G equal to 2. So this means that you have to find out number of slots. So this means number of poles are fixed because your speed is fixed. Your number of phases are fixed because you're already designing a 3-phase machine. So this means that you are going to find out S over here. That is actually the number of slots. But sometimes it can be the other way around also, that you are told, okay, this is the number of slots in your machine. The number of poles are given. You have to find out G or Q yourself over there. Ji, Hamza, kuch keh rahe?
Speed होगी, speed तो फिर design requirement में
Yes, speed is a design requirement, because ns is equal to 120 f by p, and your speed is actually quite close to this ns, this is nr. So this means your frequency is fixed, so certainly your poles are also fixed over there. So this means that this term and this term in the denominator, they are fixed. The only thing that you can change is this s, because this g can increase. And I hope so you have gone through the previous lecture that g can only have a value from approximately from something 2 to 5. The better range is approximately 3 to 4 for G, and this actually distributes the winding to 3 or 4 slots over there. Now using this G over there, since P is the number of poles, M is the number of phases over there, few terms which are very, very important. One thing is called as the coil pitch. Now if you remember, if I go back to your DC machines windings over there, this was the coil over here. So if I can mark that coil, supposedly this coil was starting from this second commutator segment, going in the first slot, going up, going down, and this was my first coil over here in this direction. Now this is the first coil over there. This is connected with segment 2, this is connected with segment 3 over there, and this is going in slot number 1 to slot number 6. Now this distance from slot number 1 to slot number 6 is called as the coil pitch over here. So you can count this coil pitch in terms of number of slots, or you can count it in terms of some units, millimeters or centimeters or whatever. Now, but very importantly, because this is a machine in which you are having 20 slots, so it's better to count them in number of slots. So you can count this one as from 6 to 1. So the coil pitch for this case, something comes out to be 6 minus 1, 5. So this means coil pitch over here, this thing, coil pitch, is actually the distance between the two ends of the coil, which are going to be measured in terms of number of slots over there. Same thing is the pole pitch, again given as YP or tau, because you have used this tau symbol in your induction machine design. So I have written this YP and tau both. And if I go back to this winding diagram over there, you can see what is the north pole. North pole at any given one point is spanning from 1 to 5. So this means that one pole is in front of 5 slots. So if I want to find out now the pole pitch, which is yp or tau, this is actually equal to the number of slots divided by the number of poles, which is s divided by number of poles p over here.
इंडक्शन मोटर में तो ये और नहीं था, वहाँ पाई डी और पी करते थे पोल पे।
That was in millimeters. Now I am measuring every distance in terms of number of slots. That was equal to pi d by p. What was pi d? Pi d was the circumference of the bore diameter, this diameter at the outside, and you divided it by p, you got yp over there. So in our case, I am measuring each distance now because we are talking about windings now. I am not talking in some dimensional parameters of the winding. So I am talking in terms of number of slots. So this means number of slots here is 20. So I am going to divide it by number of poles. Now one thing very important over here. There will be some windings which we will be discussing in the next lecture, that sometimes this 20 divided by 4 is there, you get a value of 5 over there. But sometimes you may even get 22 divided by 4. In that case, the answer becomes something 5.5 or whatever, something 5.2 or whatever. This is also possible. This is practically also possible. This we will talk about. This is a very different type of winding, and to make that winding workable, it's an even difficult task over there. But it has considerable advantage with respect to your Kp and Kd. I don't know how many of you have gone through the proof of these two, because Kp factor, if you remember, if I'm not wrong, is equal to something cos of theta divided by 2. So cos theta is actually the angle by which you are chording it. By chording, I mean, supposingly if I draw that coil over here again, supposingly this is my coil 1 end, this is my coil 2nd end, and I'm just showing it over here. So if this is my coil, so if this is my coil, supposingly this is A and A dash, this was supposingly slot number 1, and supposingly my YP, okay, YP or torque supposingly was equal to 5. For example, I'm just taking a value. So this was equal to 6 over there. So this distance between the two ends of the coil was equal to 5. And this one was your YP or equal to tau, that is the number of slots. Now, this type of winding in which you are having the starting from 1 and going up till the full pole pitch, this type of winding is called as a full pitch winding, and full pitch winding means you are covering the whole pitch of the winding, and this is the type written over here. The winding type based on the coil pitch is called as full pitch over there, which means that YP is equal to tau, or is actually equal to that they both are same. That is, the coil pitch is equal to the pole pitch. But if you can make the winding, supposingly now if I, instead of going to 6, if I make it something a little 1 slot less, which means instead of going to 6, I go to supposingly just 5 over here. Now my YC or coil pitch becomes equal to 4, which is certainly smaller than your YP. This type of winding is called as the short pitch or the coiled coil, where coil pitch is less than the pole pitch. And this angle, now the important part, I don't know how many of you have gone through this proof, this angle theta in terms of electrical, okay, in terms of electrical, so when you are going to take this Kp, this is cos theta by 2, this theta by 2, you get your Kp over here. This angle theta in electrical angle is over here theta, so this cos theta by 2 gives you the pitch factor. Now if this theta is equal to 0, certainly cos of 0 is equal to 1, so Kp becomes equal to 1. But the advantage of this theta is this, that you can have some selective harmonic cancelling due to this pitch factor. So you can have some selective harmonic cancelling over here. How this will happen, we will talk in detail when we have done the windings over there. I will tell you, we will do some examples over here in the next class, that how this theta, this is the cording angle. Sometimes you call it as theta C also. This is also theta C over there. So you can call it theta or theta T. Theta C is actually the angle over there by which you are cording over there. So this means that your winding based on the coil pitch, one is called as the full pitch, other one is called as the short pitch or the corded coil, and coil pitch is less than the pole pitch over there. Some more things over there before I proceed on towards the full pitch winding. You have phase spread over here. What is phase spread? Which means that how much angle is being spread by one phase to the other. Supposingly, if I can show you an example from one of my machines lecture. In machines lecture, if I have this, supposingly this is a induction machine. Induction machine, you can see what I have: A dash, and then I have another A dash, and then I have this B, I have this B dash, this is B, this is again B dash, then these are two are C, and I have C dash. Now, seeing this diagram, you can easily see what are this. This is a cluster of two slots having the same phase. So this means here, you can easily say G is equal to 2. This is already known. So G is equal to 2, and you can find out how many number of slots are there. How many slots are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this means your number of slots are, I'm just using SS over here. You can only use S also. It's totally up to you. I use normally sometimes, because for the rotor we have to design also. So SS is the stator slot, SR is the rotor slot. So sometimes that's why I use SS every time. So this SS is equal to 12. Number of poles we still don't know. Number of phases, that comes out to be 3, or which is actually also as M. Your G comes out to be 2 by seeing this diagram. And since your G is equal to approximately SS divided by P multiplied by M, so your G is equal to 2, P is equal to unknown, SS is equal to 12, so this is 2 equal to 12 divided by P is unknown, and I have 3. So this is 6, and I have now 2 over there. So number of poles is equal to 2. So if you calculate this one from this formula, your number of poles comes out to be 2 equal to. So the phase, now coming on to the question which I am asking you, what is phase spread? Phase spread is this angle. That is from this point to this point. A phase is spreading. So the angle, electrical, not mechanical, please remember, electrical angle from this point to this point is called as that phase spread over there. So coming back to your dam winding lecture, the phase spread is written as this symbol over here. What we call this? Rho symbol, I guess. So density, we use it rho, is equal to G gamma. And what is this gamma over there? Gamma is the slot angular pitch over there. Now, what is the slot angular pitch? This is very important. Slot angular pitch is equal to 180 degrees divided by the slots per pole. Now, how this 180 degree is coming into play? When you have your north pole and you have a south pole, the electrical angle going from north pole to south pole is equal to 180 degrees. So this is coming over here in numerator 180 degrees, and in the denominator I have slots per pole. Now what I mean by this, listen to this very carefully. I have a north pole, I have a south pole here. So supposingly in this case over here, I have slot number 1 here, then I have slot number 2 here, 3 here, 4 here, 5 here, 6 here, 7, 8 and 9, and then 10, 11, 12 and so on. I'm doing it. Now over here, mechanically you can see the angle between north and south is 180 degree. But at the very same time, since this is by chance a two-pole machine, so that's why you are getting the angle mechanical equal to electrical angle. So electrical angle between north to south is equal to 180 degree. But even if this south was not here, and supposedly this was a 4-pole machine, which means south was here, then north was here, then south was here, then still the angle between north to south is still going to be 180 degree electrical. So this numerator value over here is always 180 degree, and here this is slots per pole, which means that how many slots are there under one pole over there. So this gives you, that's gamma angle, gives you the slot angular pitch, which means if I go back to your lecture over here, where is my lecture actually? Okay, so coming on to this one, I have 12 slots. So the angle from this point to this point, this angle is called as gamma. ठीक है, इन इलेक्ट्रिकल, अगेन इलेक्ट्रिकल एंगल्स ओवर देयर, नॉट मैकेनिकल. मैकेनिकली तो हमें पता है ये पूरा का पूरा 360 है. आई हैव 12 स्लॉट्स ओवर देयर, सो द एंगल इज 30. बट इफ इन माई केस थीटा पी इज इक्वल टू 2 एंड सिंस थीटा इलेक्ट्रिकल इज इक्वल टू पी बाई 2 थीटा मैकेनिकल, यू पुट पी इक्वल टू 2, थीटा इलेक्ट्रिकल बिकम्स इक्वल टू थीटा मैकेनिकल. बट इफ पी इज इक्वल टू 4 then the equation changes. Similarly, if p is equal to 6, the equation changes. So gamma angle is this angle. This is called as 180 degrees divided by that angle over here, the slots per pole. So you get this gamma, and since you find out this gamma is found out, this angle is gamma, you multiply it by, since I am talking about this angle to this angle, this was your phase spread. So यहाँ से लेके यहाँ तक एक gamma, यहाँ से लेके यहाँ तक एक gamma. So this means you want to find out phase spread, you multiply it by G multiplied by gamma. What is G? G is equal to 2 because 2 slots multiplied by gamma over here. So this is the phase spread over here, that is given as G gamma or Q gamma, because G and Q both are interchangeably used. So this is over here G gamma or Q gamma. Now these values of phase spread, this gamma, G, YP or T or M or P, these must be known to you before you are going to start a winding. Now one thing very important, one more thing before you proceed on to the winding. Beta is the phase EMF displacement. Now I'm not going to go in much detail into this one, because whenever a winding is complete, then we can find out actually what is beta. But in formula phase, this beta is equal to 2 pi divided by m. 2 pi is in radians, because 2 pi is the whole 360 degrees, and you divide it by the number of phases. This comes out to be that radian angle between two phase EMFs, which means I am talking about that if EA is equal to this one, so certainly this means that this is going to be EB. Electrically, the angle between phase A and phase B would be 120 degree. But if you convert it into radians, then this will be 2 pi, which is actually the whole circle, divided by 3. So it's actually the same thing, nothing fancy over here. So the phase EMF displacement will be equal to 360 degree divided by 3, that is 120 in degrees. But if you want to convert it into radians, then you have in the numerator 2 pi over there. So this is the phase EMF displacement over there. हाँ, ये वो चीज़ वही है, इट्स नथिंग फैंसी ओवर देयर. बट आई विल टॉक अबाउट दिस वन बिकॉज एक्चुअली दिस इज इंपॉर्टेंट. व्हेन G equals to 4 or 5, then the whole phasor diagram changes. ठीक है, वो हम देखेंगे उसको. नाउ द टाइप ऑफ वाइंडिंग विच आई एम स्टार्टिंग ओवर हियर, आई एम नॉट गोइंग टू कंप्लीट इट, आई विल लीव इट फॉर यू टू आंसर सम क्वेश्चंस which I will open them. If you see over here, I am talking about integral slot. Integral slot here means that the integer value is used for your number of slots or the value of G over here. This is very important. G value is going to be an integer. कुछ ऐसी वाइंडिंग्स भी होंगी जहां पर हम फ्रैक्शनल स्लॉट वाइंडिंग करेंगे. दैट इज टोटली डिफरेंट वाइंडिंग इन विच आई एम गोइंग टू हैव दिस G वैल्यू इक्वल टू सपोजिंगली 2.5 और मे बी समथिंग 3.33. ये वैल्यूज भी पॉसिबल हैं, विच मीन्स द एवरेज वैल्यू इज एक्चुअली, ये ऐसा नहीं होगा कि 3 और उसमें से आगे चौथा कंडक्टर में से कोई 0.33 स्पेस निकल रहा है. नो, इट्स नॉट गोइंग टू बी. द होल मशीन सपोजिंगली हैज द नंबर ऑफ स्लॉट्स इक्वल टू 24, एंड व्हेन यू डिवाइड इट ओवर हियर दैट 24, that G value comes out to be 3.33 something. ठीक है, that's going to be average. So here I am only talking about a winding where G or Q is equal to 2. Second thing, this is a full pitch winding, which means that my YP is equal to, this means over here YP is equal to YC is equal to tau. So over here, then slots are fixed. P is equal to 4. I can find out G because I have been given slots, number of poles be given hai. I have G over here, I can find out G. It's a small machine, so G is only equal to 2. If I want to find out gamma, which is actually the slot angular pitch, 180 degrees divided by slots per pole, so this comes out to be 30 degrees. So this means in a machine filled with 24 slots, I am going to have 30 degrees over here as the angular pitch over there, and if I multiply this G by gamma, I can find out my phase spread, which is the same thing as G multiplied by gamma, that comes out to be 60 degrees. So now I have to design a winding which is coil span equal to full pitch winding and integral slot winding. Slots is equal to 24, P is equal to 4, M is equal to 3, which is actually the 3 phases, and it's a double layer winding. Now double layer winding means that each slot is going to be visited twice. Now, if you remember, those of you who still don't remember it, if you go towards your machinery course over there, we used to have a winding in which one was dark line, other one was a dotted line. One dark line, one dotted line. Those of you who can revise, please go through lecture number 9A and 9B of your EMF playlist, which I am teaching to session 2 2020. 9B is related to your double layer winding. So it will give you an idea what I am actually talking about. So over here, I have to do a double layer winding, which means I will have to make something like this, a 24 slot over here. You can see what I have done. I have done 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. This is up till 24 slots over there. But with each dark line, I have a dotted line also. So it is visited twice. So this means there are 48 vertical lines, and those 48 vertical lines are in such a way that you are going to have now 3-phase winding done. Remember, this is an open type winding in which A supposedly phase starts from here, then it has to complete that number of turns over here, whatever turns, and then end at A dash. So you will have A dash, and then similarly you will have B dash and C dash. How you connect them in series or in parallel or in Y or delta configuration is totally up to you. Now, before I proceed on and show you the winding over here, few things very, very important. A and B phase, the electrical angle between them has to be 120 degrees at all cost. This is very important. Then similarly B and C, theta electrical, again 120 degrees, and similarly C and A, theta electrical has to be 120 degrees. Secondly, very, very important that A and A dash, the electrical angle between them has to be 180 degrees over here. Now, since this is a 4-pole machine, this is the 4-pole machine, so theta electrical is equal to P by 2 theta mechanical. So this means over here theta electrical is going to be divided by 4 by 2 theta mechanical. So theta electrical is going to be 2 times your theta mechanical. Now, keep this in view that your theta electrical is equal to 2 times your theta mechanical. So you have over here this formula, and using these 3 plus this one, certainly there will be B dash, your angle is also going to be 180, C dash, your angle is also going to be 180 degree. Now, if you see closely over here, this diagram may be faulty. Okay? I'm not saying it's perfect over here. It may be faulty because I'm going to leave with you some questions over here, which I will ask you to answer, yes, tomorrow, maybe in the lab time. Now, what I have done over there, I have started my winding over here from 1. Okay, ji? I have started my winding here from 1, and I am going in the 7th slot over here. And why I am going in the 7th slot? Because what is my coil pitch or coil pitch over there? This is coming out to be 24 divided by 4, 6. Okay? So 1 plus 6, 7. I am going in the 7. So this means you can see I have gone from 1, ended at 7. And since I can do many number of turns, so this will be something like this. I will do number of turns over here, whatever number of turns I want. And this will be equal to that number of prime stator winding turns which we have already found out. ठीक है, जो आप लोगों ने स्टेटर निकाला था उसके लिए this will tell you how many number of turns you are doing. ठीक है, since this is a double layer, you will double it. ठीक है, this will be double layer, so it will be whatever number of turns you do in one slot second time. Now, if you see over here, if I will start from first slot, end at 7, and then my next winding starts at this 2, and then next coil, I am ending at 8. Now, when I am here at this point, can you tell me where I will go from here this point? Now, remember this thing. ये दो coils इकट्ठी क्यों आई हैं? This is very important. Why? Because my phase spread is equal to 60 degrees. My G is equal to 2. So 2 coils are now together. 2 coils इकट्ठी आ गई हैं. ठीक है? So you are done over here. Now question over here is it that from here this position where I am going to go, should I go in this direction or should I go in this direction? But नहीं, एक सेकेंड. You are going to go either from this point. यहाँ हमारा end point हो गया. अब यहाँ से should I go in this second slot from here and then complete the winding from this end? Why I am asking this? Now I will leave this question to you open and ask you the answer tomorrow. If I go from this end and complete this winding over here like this and complete it over there, I can end my winding at this 7th slot and this will become my A dash. Now why I am ending at A dash? This is very important. I started from 1, went on the other side, completed the winding from here, doing all the loops whatever, and ending at A dash. Now you see what is the angle between A and A dash. What is A? What is A dash? A is in first slot. A dash is in 7th slot. So the distance between them is 6. Now coming back to the data. What was the angular pitch? 30 degrees. This is electrical. So 6 into 30, 180 degrees. आपको A dash के अंदर 180 degrees का फेज डिफरेंस रखना है. Yes. बिल्कुल. अगर आप इस साइड की बजाय इधर जाते हैं सीधा, this would not be possible. Now how this is going to be connected, ये मैं आप तक छोड़ रहा हूं. ठीक है? ये आगे कनेक्टेड कैसे है? यानी कि ये एक 2 कॉइल्स का सेट, ये 2 कॉइल्स का सेट, ये 2 कॉइल्स का सेट, ये 2 कॉइल्स का सेट. So how they are going to be connected, I am leaving it to you. Secondly, B phase is starting from here, which is the 5th slot, and this is the first slot. A और B के दरमियान में कितना फासला हुआ? 5 minus 1, 4, and 4 into 30, 120. So A and B ये ठीक है. यानी कि A यहीं से स्टार्ट होना है, B भी यहीं से स्टार्ट होना है, A dash. These things, 3 things are fixed. B और A dash को निकालने का हमें जरूरत नहीं है क्योंकि हमारा बेसिकली करंट 3 फेज में A से जाएगा, A dash से वापस आएगा, B से जाएगा, B dash जो यहाँ होगा उससे वापस आएगा. हाँ, अपनी वेरिफिकेशन के लिए. हाँ, वो आप देख सकते हो. You can verify it out. Now there are some problems here in this one. Now problem is this. Well, show down. I will leave this open over here. If you see very closely in each slot, agar this is the 7th slot dark line and this is the dotted line in 7. ठीक है जी? They both are corresponding to A phase. They both are corresponding to A phase. आप देख सकते हो in every slot. यहाँ भी एक A, यहाँ भी 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 A. Similarly, this is also A, 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 this is also A. Now question over here, what's the advantage of a double layer winding? अगर एक ही slot के अंदर आपने दोनों windings एक ही phase की डाल देनी थी, तो practically तो वो तो single layer winding हो गई. नहीं, वो तो उसकी देखो डबल लेयर वाइंडिंग का फायदा क्या था? डबल लेयर वाइंडिंग का फायदा ये था कि एक A फेज का करंट हो और एक B फेज का करंट हो या C फेज का हो, ताकि आपका MMF बढ़ सके. लेकिन आपने एक ही A फेज की दोनों वाइंडिंग यानी कि दोनों कॉइल्स आपने एक ही डाल दी हैं, तो आप तो बेसिकली क्या कर रहे हो? आप नंबर ऑफ टर्न्स बढ़ा रहे हो बेसिकली. So this may be wrong. I'm not saying it's wrong. I'm leaving this question to you. Think on it. Think on it. Is this wrong? Is this connection wrong or right? ठीक है. हाँ, few things are vital which are true. A यहीं से start होना है, A dash ने यहीं end होना है और B ने भी यहीं से start होना है. Similarly, B और C की आप आगे position B dash और C dash या C जो है वो आप यहीं से निकाल सकते हो. But find out, is this correct or not? ठीक है. Think on it. Think on it because you have to find out, these rules have to be verified. ये होने चाहिए, पूरे होने चाहिए. Similarly, this has to be also verified. So think on it, how this is going to be verified and how. Achha, and one thing very important. In the exam, even if I ask you to draw a winding, and if it is supposedly not some very difficult type of a winding, and if I have to, please use colors and don't show all the phases. आप सिर्फ 2 फेज दिखा दो इनफ।
तीसरे फेज कौन सा एहसास बेचारे को मेहरबानी
नहीं, वो मेहरबानी का मकसद नहीं है, मतलब ये है कि आपकी ये पूरी वाइंडिंग क्लटर हो जाएगी। मेरे पास तो कलर्स की ऑप्शन है, आप देख रहे हो मैंने क्या किया है, आई हैव यूज दिस ब्लू ओवर हेयर, पिंक ओवर हेयर, देन आई हैव यूज दिस विल बी एक्चुअली ऑल्सो वाइट ओवर हेयर, इसको भी मैं वाइट कर देता हूँ। So this will be white and then you have green over there. I can use any other color. But in exam you won't be having that leverage. But anyway, if this question comes over there, maybe I can give you a printed sheet with vertical lines. ठीक है? Maybe. अब एग्जाम में पेपर आए, सवाल आए तो फिर ना, मतलब don't worry on that one. So, but first of all, by tomorrow, if we are talking about this one in the lab over here, kindly answer these questions which I have placed over here today. How this winding is going to be. This document file is not going to be of that much of help. Okay? Try to find it out on Google. You will have to, and then apply your brain, because I have given you all the data. This data over here, gamma is there, G is there, coil pitch or there, phase spread is there. Apply it. Okay. Or first of all, I guess the answer is very simple. You only have to go on Google and find out कि double layer winding के अंदर can each slot have AA, or it has to be AB, or it has to be AC or whatever. If A is good, then this is okay, well and good. Complete the whole winding. ठीक है? I will, ये मैं इसकी एक कॉपी आपसे शेयर कर देता हूँ इसकी, ये पूरी वाइंडिंग की with the vertical lines एक white page के ऊपर, so you can do it yourself. So tomorrow, try to bring this one with your winding done. I am only asking for the integral slot winding. The next class we will talk about this fractional pitch winding over here, which is integral slot, but here it will be fractional pitch winding.
फ्रैक्शनल पिच बैलेंस करना उसको मुश्किल
बहुत मुश्किल है, it's very difficult. Fractional pitch को बैलेंस करना is like and one thing very important, in fractional pitch these angles also don't agree. हाँ, वो फ्रैक्शन में है तो द एंगल डज नॉट कम 120, इट कम्स आउट टू बी 108 समटाइम 110 और मे बी 189 और 90 और समथिंग लाइक दैट, वो प्रॉब्लम आती है। लेकिन द एडवांटेज इज एनॉर्मस. The advantage is that you can actually cancel selective harmonic, because this Kp factor is given as over here as cos theta by 2. But if you have supposingly your theta c is supposingly equal to 30 degrees, for example, then if you have a third harmonic, you want to cancel it. Supposingly it's not connected in y में होगा तो automatically third harmonic वैसे ही cancel हो जाएगा. But if you want to calculate Kpn, this will be equal to cos n theta by 2. So the formula you can selectively cancel it. क्योंकि अगर आपका Kp 0 हो जाएगा उस हार्मोनिक के लिए तो ऑटोमेटिकली आपकी वोल्टेज जो आपका फार्मूला था EPH was equal to 4.44 F into 5, हाँ वो आपका ऑटोमेटिकली EPH 0 हो जाएगा. तो थर्ड हार्मोनिक, फिफ्थ हार्मोनिक, सेवंथ हार्मोनिक, they will be cancelled. So please kindly, I will share this document on MS Teams also. I will share this one. मैं ये delete करके बल्कि इनफैक्ट इसको कर दूंगा ताकि आप लोग उस पर खुद बनाओ, but use color pencils. ठीक है? So this is all for